Hello, everyone. I am Shih-Shinh Huang from National Kaohsiung University of Science and Technology, Taiwan. Today, I want to talk about a texture descriptor called the HLID, short for histogram of local intensity difference. This descriptor was firstly proposed in IEL Electronics Letters 2013 and especially suitable for pedestrian detection in far infrared FIR thermal images. The outline of this lecture includes introduction about the origin of HLID, gradient computation about how to use intensity difference for gradient computation, block description about how to describe the texture of a block using HLID. Detecting pedestrian in images is an important topic in many applications. Besides designing a good classifier, extracting effective features to describe pedestrian is also critical in pedestrian detection. Currently, HOG proposed in 2005 is a widely used texture feature in describing pedestrian appearance in visible images. However, HOG may be not suitable for far infrared images because of two factors. Firstly, compared to visible images, temperature changes in pedestrians are not significantly, so that the intensity distribution of far infrared image is smaller than the one of visible image. This phenomenon can be seen according to these two intensity distributions of the same rectangles in visible and FIR images, respectively. Secondly, since far infrared camera captures low frequency, so that far infrared images generally lack of texture information. Accordingly, the proposed HLID use intensity difference instead of spatial filtering to compute the gradient information. As HOG, HLID is a kind of features that describe the texture of block in the form of histogram of oriented gradient. The horizontal axis is the bin index of gradient orientation. Vertical axis is accumulation volt of gradient magnitude. But HLID differs from HOG in the way of computing the gradient orientation and the magnitude. Next, we will talk about how to compute gradient orientation and the magnitude in HLID. In HLID, the gradient magnitude of a point P is defined as the maximum intensity difference around its neighborhood. For a 4x4 block, the gradient magnitude of an interior point P is computed as follows. Firstly, compute the difference between east neighborhood, northeast neighborhood, and so on. Then, we pick up the maxima of these 8 numbers as gradient magnitude of P. For gradient orientation, it is defined as the direction to its neighborhood with the maximum intensity difference. For the aforementioned example, the gradient orientation of point P is the southeast because it has the maximum intensity difference to its southeast neighborhood. For each point in the block, we compute its gradient magnitude and the orientation one by one. Then we can obtain the gradient magnitude and the orientation of this block. Having magnitude M and the orientation theta in hand, we next talk about how HLID describes the texture of this block. Here, we give the overview of the HLID descriptor for a block B. Firstly, the block B is divided into 4 cells, and each cell is described by an 8-bin histogram of oriented gradients, called the cell descriptor. Then, these 4 cell descriptors are directly concatenated to form a 32 histogram, which is called the block feature. By taking the top left cell as an example, we next detail the way to compute the cell descriptor. The idea behind is through the voting mechanism. By taking theta as voting index and n as voting weight. For example, the orientation of the first point in this cell is northwest. The magnitude is 2. So we add 2 volts to northwest bin. For the next point, it is with north direction and the magnitude 2. Similarly, we add 2 volts to north bin. By visiting all points, we can obtain the 8-bin histogram of oriented gradients as the cell descriptor. This 8-bin histogram can be viewed as the 8-dimensional feature vector. After obtaining the 4 8-dimensional cell feature vectors, we concatenate them to form a 32-dimensional block feature vector. Furthermore, to be invariant to gradient scale, we normalize the block feature vector to unity by dividing a normalization term, z. L1 norm and L2 norm are both the weights for normalization. Their definitions are expressed as these 2 equations, respectively. In this lecture, we detail a HLID texture descriptor for pedestrian detection in far infrared images. Thanks for your listening and have a nice day.